Okay, so for this polynomials problem, let me start by reviewing something real quick, right? So if we have 2 points, we can put a line through that, right? Here, this is degree 1, but we have 2 points. And if we have 3 points, that uniquely identifies a parabola, right? So we have degree 2, but we have 3 points. So if we have, for example, degree D, right? Um, then that means that we need D plus 1 points in order to uniquely identify that. So I guess this is a quick trick that I use to help me out. Um, okay, so how many distinct n-degree polynomials are there, right? In this problem, an n-degree polynomial kind of looks like this. an to the power of xn plus an minus 1 to the power of n minus 1 plus, all the way to a 2x squared plus a 1x plus a 0. All of the AIs are just constants. All of these are just constants. Now, how many options do we have? We have, okay, at first glance, we might say we have, p options for this, right? 0 all the way to p minus 1, right? Those are the distinct numbers in GFP. So we have, you know, P options for the first one, P options for the second one, all the way to P options for A0. So you might say P times P times P dot 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 times P. How many are there? There's N, but also there's the 0, right? So we have N plus 1. So this is actually P to the power of N plus 1. And this is almost the answer. The only thing is that in order for this to actually be degree n, we need this first term to be non-zero. That means that this term, this an, cannot be 0. So an cannot be 0, which means that we have p minus 1 options for an, and we have p options for the rest of them. So p minus 1 options for an, and p options for the other n coefficients from n minus 1 to 0. So that's what it is. Now, going to this one, how many distinct polynomials have at most, now this is at most degree n. So that means that an can be 0. We don't have this restriction anymore. So we have p options for an as well as everything else. So this is simply just p to the power of n plus 1, which is what we thought the original answer was, this thing right here. Okay, how many distinct polynomials of degree at most n are there such that p of 0 equals 1, p of 1 equals 2? Okay, remember, we have now this is essentially the same as saying, 0, 1. This is 1 point, right? And then 1, 2. This is another point. So far, we've specified 2 points. And, if we have degree at most n, that means that we can have n plus 1 points, right? We need one more number of points in order to specify a degree n polynomial, right? And if you're looking at the at most n and you're like, oh, do we have to consider the other cases where it's not n plus 1 points, but we're only specifying, let's say, n points or n minus 1 points or something? Um, well, no, because if you think about it, if I have this line here, right? 2 points uniquely identify this line, but I could have used 3 points, but the third one is just redundant, right? And that's what this is saying. Like if I can just like look at n plus 1 points, and that's, maybe some of them would be redundant or something, but that would take care of this at most part of it. But yeah, small side note there. Let's go on. So we have n plus 1 points, right? That we need in order to identify a degree n polynomial. We already have 2 points identified here. So the degree of freedom, I guess, so to speak, is like n minus 1. We can choose n minus 1 of those points. And for each of those points, we can choose, we have, you know, for example, if the input is 2, um, we have P options for this output thing here, right? And if it was like 3 was the input, we have P options for this as well. right? So we have like n minus 1 points that we could possibly specify, and there's p options for each of them. And the answer is just p to the power of n minus 1. Okay? And then this last problem here is a bit of a longer one, but it requires a little bit of insight. So, um, we have this thing right here, x minus 2 times q to the power of q of x, which is equal to x times q of x minus 1. Okay. So we see this like a intimidating thing or whatever, right? But really, we're at an advantage here because we know that this has to be true regardless of what input x we feed it, which means that we can feed whatever value of x makes our lives more, uh, easy or whatever, right? The thing is, I see this x over here, right? So to start off, what we can just do, what if we say x is equal to 0? Just plug in x equals 0 into this thing, right? Okay, let's see. So this becomes negative 2. This is q of 0, right? So negative 2 q of 0. And the reason I plugged in the x was because the other side is just going to be 0. 0 times something, which is just 0, right? Is equal to 0. This means that q of 0 is equal to 0, right? Now, if q of 0 is equal to 0, let's scroll up a little bit. This is what an n-degree polynomial looks like, right? If q of, or like if you plug in x as 0 here, this becomes 0, right? This becomes 0 because 0 to the power of n minus 1. Everything becomes 0, except for this last term that doesn't have x in it, right? That means that this last term is 0. In order for q of 0 to be 0, the last term, the constant term, has to be 0, right? And yeah, so in order for that to happen, the constant term is equal to 0. Okay, what does that mean? That means that, first of all, it means that 0 is a root, right? Because it makes the thing 0. Um, the other thing is that all of this stuff is what q of x is, right? That means all of these things have a common factor x in them, which means that I can kind of pull that x out. So it's like, as an example, if q of x was like x squared plus 5x, right? There's no constant term here. What I'm saying is I can pull out the x and I can write x plus 5 here. So it's like x times something, where that thing is degree 1 less than the original thing, which is 1, degree 1. This was degree 2, and then this is now degree 1, right? Is x times something that's degree 1. So over here, the degree um, of q, right? So the degree of q, so we have q of x, right? This is equal to x times some other polynomial. And I guess in the solution we call it like x1, sorry, q of 1 of x. Um, and all we're trying to say here, in this example, this would be q of x, right? And this thing right here would be q1 of x. Basically, it's degree 1 lower, right? If this is degree n, then this would be degree n minus 1 because you take out the x right there. Okay? So what we're saying is let's like substitute this thing back into the original expression. Okay? So x minus 2, um, and then, oh, by the way, if I plug in x equals x minus 1, what I mean is like instead of plugging in x, I plug in x minus 1 into this thing right here. What I get is q of x minus 1 is equal to x minus 1 times q1 of x minus 1. Okay? I'm going to plug that into this part of it right there. So x minus 2 times q of x. Q of x we said is equal to x times q1 of x, which is equal to x times x minus 1 q1 of x minus 1. Okay. This might seem like bigger, but I promise you we're getting to kind of like a solution here. What if now we plug in 1 into this, right? We plug in 1. Now the left-hand side becomes 1 minus 2, which is negative 1. We plug in 1 for x, right? So that's just 1. And then q1 of 1, right? We say x is equal to 1. And the other side is just 1 times 0, and then, we don't care about anything else. Now this thing is just 0, right? Which means that if we can kind of get rid of this because the other side is 0. q1 of 1 is equal to 0. Okay. So that means that whatever this smaller polynomial was, right? It basically has a root of 1. So that means that we can, similarly as we did before, right? We can actually write q1 of x, right, equal to x minus 1 times q2 of x. We can take this x minus 1 out because 1 is a root of the polynomial. And like this is the fundamental theorem of algebra, which says that x minus, root 1 times x minus root 2 times all the way to x minus root n. This is enough to describe your n-degree polynomial, right? You just multiply out all the roots. And that's what I'm doing here. I know that 1 is a root because if I plug in 1, I get 0. So I can take out an x minus 1 over here. And by the way, if I were to put in, I rewrite this thing, but I put in x minus 1 instead. I get q1 of x minus 1. That's equal to x minus 1 minus 1, which is x minus 2, times q2 of x minus 1. I'm just rewriting this thing, but putting x minus 1 in it instead of x, okay? Everywhere that's x, I'll just like place x minus 1. So we had this thing. This was our evolved equation. I'm just going to do the substitution of this thing and this thing over here, right? I'm going to write x minus 2, right, from here. X minus 2 times x. Okay, q1 of x. q1 of x is equal to x minus 1 times q2 of x. Okay? And this is equal to x times x minus 1 times q1 of x minus 1. That's why I replaced everything with x minus 1 in order to get this expression right here. So I'm going to replace that here. X minus 2, q2, x minus 1. Okay, cool. So we see that we have a lot of terms here that are the same. On both sides, we have an x. On both sides, we have an x minus 1. On both sides, we have an x minus 2. Now, we can't cancel these on both sides unless we know that x is not equal to any of, 0, 1, or 2, right? If x is equal to 0, then we have like 0 equals 0, and we can't cancel that. That's not a legal thing to do in algebra, right? So, and we have to also make sure that x is not equal to 1 and that x is not equal to 2, right? But if it's greater than 2, suppose x is greater than 2, it's just not equal to any of these things here. Then we can cancel x on both sides. We can cancel x minus 1 on both sides, and we can cancel x minus 2 on both sides because it's not any of these things here. So it's not 0 equals 0. That will give us q2 of x equals q2 of x minus 1. Now this is weird, right? Like, suppose x is equal to 3. It can't be one of these, right? So I'll say 3. So, oh, sorry, yeah. That means that q2 of 3 is equal to q2 of 2. So we have some polynomial that if you feed in 3, that's the same as feeding in 2, right? Okay, let's plug in x equals 4. Then that means that q2 of 4 is equal to q2 of 4 minus 1 is 3. So wait, that means that q2 of 2 is equal to q2 of 3, which is equal to q2 of 4, which is equal to q2 of 5, which is equal to q2 of 6, and so on and so on. So from this, we get that q2 of 2 is equal to q2 of 3, which is equal to, I was right, q2 of 4, which is equal to, all the way. Well, this can't be the case, right? Unless this is a constant, unless they're all equal to a constant, c. So q2 is a constant. So q2 of x is a constant. So we know that q of x, q1 of x is equal to x minus 1 times q2. Q of x is equal to x times q1 of x. So real quick, q of x is equal to x times q1 of x, which is, x minus 1 times q2 of x. And and by the way, we know that this thing is a constant, right? Constant. So we have that this is equal to c times x times x minus 1. And our only degree of freedom, so to speak, is the c. So you can only choose this to be one of p values. And I believe that should be the answer. Yeah. So what did it ask in the beginning? It asked find all polynomials. Okay. Yeah, so this is what any polynomial of q of x would kind of look like. That's your answer. Where this thing is, something that is 0, 1, 2, all the way to p minus, I should say minus 1. Yeah.